And can I stand from this other side? Everything okay? Can I start? Okay, so hi everybody, I'm Carmine from the Barkhausen Institute of Dresden. Today we talk about our ongoing work on building compilers that preserves all the properties that you can prove in a weakest precondition calculus for your source language. But I have to put this one. I guess. Does it work? No. Okay, then I will just stand next to the laptop. Okay. A second. All right. Okay, but let's start by giving you a bit of the context in which we are working. So at the Barkhausen Institute, we are developing a framework for the verification of Rust programs. And if you're curious, you can take a look at our paper at PLOS last year. The framework works as follows. You write your program in Rust, you implement your program in Rust, and this gets transpiled into ROC. You can give a specification for your program, and you can prove this specification in the weakest precondition calculus we implemented in Iris for our language. This is a very small example, but on the long run, we plan to formally verify the whole unikernel. There is a project called Formula 5 in case you are interested. Of course, we don't want just to verify our Rust programs, we also want to compile and execute them. And we are interested mainly in two targets. One is an extension of RISC-V with compartments. Another one is a cloud architecture. Of course, since we spent a lot of effort in building a program logic and verify source program, we would like to preserve the specification that we proved in our calculus. And the question is, of course, how we plan to do it. So we are relying on interaction trees that I will briefly try to recall in one slide. So interaction trees or I trees are a general purpose data structure that you can use to represent the behavior of effectful and possibly non-terminating computations. I like to visualize them as infinite trees, and on the nodes of these trees you can find either an event like read or write, or you can have some other kind of nodes that represent internal computation that don't have any externally observable event. There are these silent steps. And you can have terminating nodes like leaves that instead represent a terminating computation that returns a value, so like this, return R. I will not recall all the nice properties of I trees, but I would like to notice that the I tree that you see in the slides at the moment doesn't have any particular meaning, because read and write are just symbols so far. But we can, of course, give it a computational meaning by interpreting these events in a monad, for example. And you can interpret read and write in a state monad, and now the I tree on the slide will represent a stateful computation. For the purpose of this work, we are not only interested in the computational meaning, giving a computational meaning to I trees, but we are interested in assigning it a logical meaning, because we want to talk about the weakest precondition calculus. And we are using a recent work from Popol last year, Program Logics a la carte, where the idea is basically you just need to specify pre and post condition for the triggering of an event. So for example, here maybe I simplified a bit. To trigger a write event, you need ownership as precondition, ownership of the location to which the variable y is pointing to, and you will return as post condition this ownership with the updated value. So once you specify this pre and post condition for each of the events you can trigger, then you can easily get a weakest precondition calculus for your programming language, given that you gave an I tree semantics for it. And quite interestingly, and also I would say a result that we all expect, is that if two programs are denoted with I3s that are bisimilar, then the properties that you can prove for one programs also hold for the other programs, of course, in this weakest precondition calculus. And at this point, as you might have guessed, we want to use these as proof technique to show that our compiler preserve the weakest precondition calculus, the weakest preconditions that we proved in our calculus. Of course, you just need to show that source and compile programs are denoted with bisimilar I3s. So to put everything in one single picture, we are defining, we are giving a formal semantics with I3 to our source language. And from that, we are deriving a program logic in the form of a weakest precondition calculus. We are doing the same for the target language. And then to verify that our compiler preserves the specification proved in the source, we will show that source and compile program are denoted with bisimilar I3s. Of course, this is a nice story, but it's very high level. There are several challenges that we are facing and that we still have to solve. But let me get to them with some order by telling what we so far think to understand, at least. So first of all, we know that we can design program logics in a kind of very modular fashion once we have a I3 semantics. No? You just have to specify this pre and post condition for each event. And if you want to add a new effect to your language, you just have to add the, just have to specify the pre and post condition for the new effect, right? And there have been very large projects like VLLVM and more recently Jasmine that gave a formal semantics to realistic languages. And in these two projects, people certified compilation steps by showing bisimulation of I3s, so adopting the proof technique that we are also considering. There are, however, they are facing, of course, our same challenges that are mostly related to the fact that values of the two of source and target languages, and of course each intermediate language, can be different. Memory representations, memory layout can be different. Effects, events can be different. And so in the LLVM project, I understood that they face these problems by a so-called layered interpretation approach. So they reinterpret source and target I3s into a common layer where they can show a bisimulation. Of course, this would be not really the best for us because we would preserve the weakest precondition only up to this common layer while we want to go all the way down. More recently, in the Jasmine project, the authors introduced more liberal notion of bisimulation that allows you to relate I3s that are also structurally different. In particular, they can relate an I3 that terminates with an undefined behavior with an arbitrary continuation. That is actually exactly what you want to do in compiler verification. We will probably follow a bit this path, but in this case, the challenge is that you need a more precise description of what's the property that holds after compilation. We plan to reuse some previous work from the past, but still the full details have still to be worked out, and here we are dealing with a resource-aware logic, so there are some non-trivial differences. And in our PriSC submission, we describe these challenges in a much simpler setting rather than Rust. We consider a toy imperative language that I guess you're all familiar with, IMP. And as target, we consider a toy assembly language. This is the same of the original I3 paper. And instead on the right, we are using a communicating sequential processes. That is a process calculus language by Tony Hoare. So you can take a look at the PriSC abstract and you will find a link to our GitHub repo, but we are not planning to push on the repo nor to maintain it. It's just to describe the challenges and the idea. And with this, I'm happy to take any suggestion, questions. Yes, it was fast.
So you took only 10 minutes.
Yeah,
instead of 15. So
I want to take questions.
we have actually time for questions, and we will not even be late for lunch. So.
Thank you. I have one maybe surface level understanding question.
Yeah.
You mentioned that you're not interested in interpreting the effects into actual monads and you just want to specify them. One thing I'm curious about is that when specifying semantics with I-trees, it's often, non-trivial to find out the order in which we interpret the effect because the monads don't stack, the monad transformers don't commute. So there's interactions between the effects that are non-trivial. But you mentioned that in your case, you can just add new specifications for new effects if you want to add them. So does that allow you to bypass the difficulty of interference between the effects? Or?
I would say yes, but we are basically just user of this program logics a la carte. So maybe this is a question for the authors of that work. In this framework, you just need to specify the pre and post condition for each effect and show an adequacy theorem. So this is maybe what you're talking about. So you have to show that somehow there is an adequacy with the previous existing effect.
All right, that might be it.
So very nice. That can be an interesting proof.
Right, thank you.
Any other question? No? So actually, I have a question. So they are, interaction trees are one among several formalisms that more or less try to express this kind of notions. Have you tried some alternatives? What are the pros and the cons?
Sure. Yeah. So this is something. Maybe this is the only question for which I don't have a backup slide, but I've been thinking about it, of course. Like the more natural would be probably using some trace-based approach. But for that, so what would become? Let's try to think of what to do there. You need a trace semantics for your programming language. Then you need to build your program logic by looking at that trace semantics, right? And then you need to show some preservation of this. So it's something that is in this I3 framework is given by one single framework. Is in particular getting this program logic seems to be not too complicated, while with a trace-based semantics you should do a lot of work to instantiate iris from a small step operational semantics. At least this is my take. Plus, of course, maybe the advantage would be that you would reuse some trace-based criterion, trace-based proof technique to verify your compiler. But still, then you will have to find a connection between the traces of the target and the properties that hold in the target.
And you do not have any problem with termination because you're doing weakest precondition, not weakest liberal precondition. No issues with termination.
So I believe this is the calculus that you get here is partial.
Partial correctness.
Yeah, partial correctness.
Okay. So I think we can text this.
Hi, thank you for the talk. So are you gonna build your own Rust compiler, or are you gonna be like the existing one?
I see people smiling in the audience. No, we are going to build our own. At the moment, we have some pieces, the very hard, like the upper part of the compilation chain, almost implemented from. Let's say, how much familiar are you with the compilation chain of? Okay, so there is the first intermediate language is called typed high-level intermediate representation. The second one is called a MIR. Mm-hmm. So we are, I don't know, MIR, medium, I don't know. We are implementing, of course, first from tier to MIR. Okay. And we will try to apply this technique there. And then we will, at some point, we might resume to some existing compiler just to have a first working compilation chain. But yeah, the idea is to go all the way down at some point.
And all the way down, would you take also existing formal semantics for the the target, like RISC-V, I'm thinking about SAIL.
Yes.
Yeah, that would be super cool.
That would be super cool. We agree. The only and this is also what we would hope. The missing brick, I would say, is that SAIL doesn't come with I3s.
Yeah.
So we would have to adapt, or I mean, we are still keeping on the table the fact that we can compare with some trace-based approach. So SAIL, I believe, maybe you can get some traces more easily than I3s. So we'll see. We are still at early stages of this compiler.
No other question? So I think we can take the speaker again. No, there's yet another one? Okay.
Yeah.
This thing's in offline. Okay. So maybe I missed something, but the bisimulation is necessarily needed in your proof chain, because in many cases we just prove one side of simulations and for compiler correctness. So
For this, I have a backup slide. Not really fitting completely your question. Well, so there is something that I was not really explicit. This rule that I mentioned that says that if two I3s are bisimilar, then the WBs are the same. So this is a homogeneous bisimulation, so very strong. But it's still useful. It's still useful when you can embed the source events into the target. And if you look at our PriSC submission, you will find, well, first of all, a program optimization input to imp, but also a imp to CSP, that more or less a CSP embed imp, in which we can use this lemma, this rule here. You need it. We are also open to explore one-way simulation. The point is that there is a lot of technical work to define these simulations and bisimulations in over I3s. There is a lot of work to be done in ROC. Show trivial stuff like preservation through bind and return, respect all the monadic stories and interpreter and whatever. If you are familiar a bit with I3s, you might know what I'm talking about. So we are trying to reuse as much as possible what's there and try to implement the least possible extension.
yeah, thank you for answer.
But yeah, I would say, in principle, we are interested only in one implication here. And also for me, it's very natural to just require one-way simulation.
So you can really thank